be solving one more problem. It's an I section. Please keep your calculators in front of you so that you can tell me, you can be quick with regard to the calculations. And it has dimension of the bottom flange has dimension of 100 mm, and it has a thickness of 20 here. And the web has a height of 100 mm. And again, thickness of 20. And top flange has 60 mm width. And it has again 20 mm thickness. You can see if we have to divide this very I section into different rectangles, we can simply do it by just making this one as rectangle number 1. This will be your rectangle number 2. And this will be your rectangle number 3. Right. And we also here what we have to find out, we have to find out moment of inertia. We have to find out moment of inertia of section about horizontal axis. About horizontal axis which is passing through center of gravity. Passing through CG, center of gravity of section. Okay. We simply have to find out moment of inertia. Right. Now here in previous problem, we had to find out the moment of inertia about x-axis and y-axis. Right. Here what is it asking? He is asking we need there is a need of calculation of moment of inertia of this whole section, right, about the horizontal axis, right, and that axis is passing through the center of gravity of the section. We don't know where is that center of gravity of this very section. Now, as you can see from the figure itself, it is symmetrical about one axis. Which axis? It is symmetrical about this y dash axis, right? Therefore, you can simply say that the moment, the center of gravity or the moment of inertia will actually lie on this y-axis. It will definitely lie, since CG also will lie there, and the moment of inertia will also lie on this y-axis. But at what distance from this point? Let's say this is our reference line. If this is our reference line, base of the bottom flange, right? Base of the bottom flange is our reference line. Sorry, RL. Now, what we need to do here, as we already know, we had divided this I section into 3 rectangles, right? And we also know that this whole section is symmetrical about y-axis, and it has been divided into 1, 2, and 3 rectangles, and the reference line is the bottom flange of the axis of is the axis of reference. Now, firstly, what we need to do, we need to find out the details of rectangle 1. Rectangle 1, as we know, what is A1? It will be simply area, which will be 60 cross 20. That will be equal to 1200 mm. And then Y1 of this rectangle, Y1 of this rectangle, and where is the reference line? It is at the bottom. It is here. It is at the bottom. Therefore, reference line will be simply equal to the bottom flanges 20 width plus web is how much? It is 100. And then we have this top flange 1, which is marked as 1. it will be at its center, that is 20 by 2. Therefore, it will be 120, 130. And then we have rectangle 2. Rectangle 2 will be simply A2 will be how much? 100 cross 20. That will be equal to 2000 mm square. And y1, y2 will be simply equal to 20 plus height of the web is 100 by 2. That will be equal to 70 mm. And then we have rectangle third. It will be simply A3. That will be again 100 cross 20. That will be equal to 2000 mm over square. Sorry. And y3 will be at its center. That is 20. Is its total depth. 20 by 2 will be equal to 10 mm. Okay, this is with regard to the areas and centroids or centroids, center of gravities of these particular rectangles, rectangle 1, rectangle 2, and rectangle 3. Now what we are in need of, now we can simply calculate what? Distance between the center of gravity of the section and the bottom face. Now we have 3, therefore we can easily calculate what? Distance between center of gravity of whole section, right? Of section. Here what we calculated, y1, it was actually for individual triangles. Rectangles, rectangle 1, rectangle 2, rectangle 3. And now for the whole section and bottom face and reference line RL, it will be equal to y bar, that will be equal to A1 y1 plus A2 y2 plus A3 y3 divided by A1 plus A2 plus A3. Now give the values of all your details and tell me what is the value of y bar. Give it quickly. Tell me how much is the y bar. Be quick.
60.76.
Okay, I guess Zarka is telling 60.76. Okay, 60.76. Let it be 60.8. 60.8 mm. This is what distance of between the center of gravity of the section, whole section, and the reference line. Now what we need to calculate is moment of inertia of all of these rectangles. Now we need to calculate what? Moment of inertia of rectangle 1, right? About axis which is passing through center of gravity, right? Now finally what we need to calculate, we need to calculate the moment of inertia about the axis which is passing through the center of gravity, and it is also parallel to what? X-axis. But we need to ultimately calculate it for the whole section. But before that, we have to look for individual rectangles, which is rectangle 1, rectangle 2, and rectangle 3. Moment of inertia of rectangle 1 about axis which axis through its which is through center of gravity through CG, and it is parallel to x-axis. We are actually checking here for those center of gravity which are parallel to axis, because we already know this section is symmetrical about y-axis. That means we already got to know that it will center of gravity or the moment of inertia will lie on the y-axis, and it will be at a distance, some distance from the reference line, which will be in the coordinate of x. Therefore, we can simply here say as I, let's name it as IG1, will be equal to BD cube by 12 for rectangle 1. Rectangle 1 is this topmost fringe, which is B. How much is B? It is 60. And how much is depth? 20 cube by 12. That will be equal to 40 into 10 raised to the power of 3 mm4. Okay, this is now moment of inertia. This is the moment of inertia of rectangular axis, right? And now we need to know, as we have already calculated the center of distance between the center of gravity and the bottom face, which was y1, it is 60.8. Therefore, you can say your y1 here is equal to 60.8. It is, what is it? It is basically the distance between the center of gravity and the bottom face. That is this. Let's say it is somewhere here. Now, what is this y1? Oh, sorry, y bar. It is y bar, not y1. Y bar is basically a distance between the reference line, that is the bottom face, and the center of gravity of the section now, which we have calculated 60.8. Now, for triangle 1, we need to calculate what? Finally, what we need to calculate, we need to calculate the moment of inertia, right? We need to calculate the moment of inertia about x-axis, for which we have already calculated the moment of inertia about an axis which is through the center of gravity, and it is parallel to x-axis, which comes out to be IG1. And then we also need distance now. We need distance between center of gravity of rectangle 1 and x-axis. And x-axis. How much is that? Let's name that as h1. That will be now which distance? You already have how much distance as y1? How much is your y1? How much was y1? Y1 was 100, 120, 130. Y1 was, it will be y1 minus y bar. That will be equal to y1 is 130 minus y bar. How much is it? 60.8. You got it. Why did we calculate h1? H1 is actually h1 is, this was our y1 for rectangle 1. Sorry. Y1 was this distance when we are talking about rectangle 1. The line in the pink is your y1, and deducting it the distance of y bar, right, gives us what? This distance, which is from the center of the gravity to the center of this rectangular section, which gives us the actual lever arm, actual height of the center of the gravity and the x-axis. Okay. Now, therefore, when we have to calculate the moment of inertia now, moment of inertia of rectangle 1 about x-axis, that comes out to be I g1 plus ah square. Okay, a1, but a1 and h1 square. Now you know how much is ag1, that is your bd cube by 12, that comes out to be 40 into 10 raised to the power of 3 plus area 1, a1, how much is it? Area 1 will be 60 into 20, 1200 into h1 square. Now how much is h1? That comes out to be 69.2 mm into 69.2 raised to the power of 2. This is your moment of inertia of rectangle 1, which is equal to 5, 7, 8, 9 into 10 raised to the power of 3. mm4. Okay, this was regarding the moment of inertia of rectangle 1, which is the top flange. Similarly, now you have to calculate the moment of inertia of rectangle 2 about an axis which is passing through the center of gravity and parallel to x-axis. About x-axis. Now for rectangle 2, I g2 will be again bd cube by 12, bd cube by 12, that is equal to as how much is your b? It is 20, and d is depth, which is 100 cube divided by 12, that is equal to how much? 1666.7 into 10 raised to the power of 3 mm4. And how much is your h2? h2 is now how much? What is y1? y2, sorry, y2 minus y bar. y2 was 70 minus 70 minus 60.8, that comes out to be 9.2 mm. Therefore, your moment of inertia, a rectangle 2 about x-axis. Sorry, ig1 plus a2 h2 square. ig2, sorry, ig2 will be equal to how much is ig2? 166.666.7 into 10 raised to the power of 3 plus area. How much is area? 102, it is 2000 multiplied by 9.2 raised to the power of 2. That comes out to be 1836 into 10 raised to the power of 3 mm4. This is your moment of inertia of rectangular 2 about x-axis. And this was moment of inertia this was, what was this? This was moment of inertia of rectangle 2 again about an axis which is passing through the center of gravity, which is passing through the center of gravity, CG. And that comes out to be BD cube by 12. Right, and this moment of inertia also is parallel to the x-axis, because we're calculating the reference line from the bottom, and the coordinates comes out to be an x-axis. So Ig2 is moment of inertia about an axis which is passing through the center of gravity, and this is actually moment of inertia of rectangle 2 about x-axis, about x-axis. Okay. Now, again, similarly, we have a third triangle, and we calculate what? Ig3. Ig3 is now moment of inertia of rectangle 3 about an axis which is passing through center of gravity. Okay, this is CG, which is passing through center of gravity, which comes out to be BDQ by 12. But we have to calculate it about x-axis. We have to calculate it about x-axis, where for which the reference line has been kept at the bottom of the bottom flange. Okay, that is why the distance is getting added up. Here again, Ig3 is BDQ by 12, and that comes out to be B is how much? 100 into D is depth 20, Q by 12. That is BDQ by 12. That comes out to be 66.7 into 10 raised to the power of 3 m4. Okay. Now we again need what? H3. H3 is the distance which is to be considered while calculating the moment of inertia about x-axis, which is the difference of the center of gravity of the whole section and the center of gravity of that particular rectangle for which we are calculating. Okay, and that is here how much? It will come out to be y bar minus y3 minus y bar. Now that it is in the downward direction, it will come out to be y bar minus y3. That will be equal to y bar is 60.8. 60.8 minus y3. How much was y3? It will be 10. Total difference. That means it is 50.8 mm is your distance. Okay, therefore you can calculate your moment of inertia in y-axis for rectangle 3 as Ig3 plus A3 H3 square. That is equal to, giving the values will give us 5 2 2 8 into 10 raised to the power of 3 mm 4. Okay, this is the moment of inertia of rectangle 3 about x-axis. Fine. Now the moment of inertia of whole section. Now moment of inertia of the whole x-axis about for the whole section, or whole section, that will be summation of all the moment of inertia. Let's say this is Ixx3, this was Ixx2, and the previous one was Ixx1. This is Ixx1 plus Ixx2 plus Ixx3. That comes out to be summation of all the moment of inertias of the rectangular section about the x-axis. That comes out to be 12850 into 10 raised to the power of 3 mm4. This is your summation of all the moment of inertias about the x-axis, right? And then you have the summation, and which gave you the total moment of inertia. Okay, this was regarding the moment of inertia of I section. Okay, is Mahvish audible? Mahvish, are you able to hear me? Mahvish, are you there?
Who is Mavish?
I don't know. It's somebody.
अच्छा Mavish from all class.
Huh?
Okay,
Yes,
so understood.
Mahvish.
Mavish from all class.
Roll number 44. Roll number 44. Mahvish, are you able to hear me?
So her mic is on, but we can't hear her. I think it's that issue I faced yesterday.
Maybe. Burhan, are you there? Burhan, roll number 61. Burhan, are you able to hear me? Okay. Talib, roll number 48. Talib, roll number 48. Sahil, what is it? Nobody is replying back.
So no idea.
Uzar, roll number 53.
Yes, sir.
Abdul Basit,
Hello.
roll number 10. Who is roll number 10?
Sir, total हमारा
Huh? Sahil, yes, repeat it again.
सर टोटल हमारा 12853 आ रहा है. आपने लिखा था 12850.
12853.
हाँ.
Fine. That's a minor issue. You can make the appropriate calculations.
Okay, sir.
Okay, fine. We'll carry on. Now, there is one more section which you will do at your own place. This is homework for you. We have a L section. Again, 20 is its thickness. Hundred mm, and then we have this as 80 mm. Total is 80, and again this is 20. And we need to calculate here again moment of inertia, about moment of inertia. Centroidal, x-axis, and y-axis of angle section. Now you can see that you have to calculate it in both the axes. You don't have any symmetrical. You cannot say that this section is symmetrical to one of the axes. Here what we have to do, you have to calculate the data in both the axes. You have to calculate ixx, you have to calculate iyy. right? In both the axes. It is not asymmetrical in any of the axes. So, firstly, you will calculate moment of inertia about centroidal x-axis, right? Then you will calculate the moment of inertia about centroidal y-axis. That means you have to repeat all the process twice. First in x-axis and calculate the moment of inertia. Firstly, when you are calculating the moment of inertia in x-axis, you will check for rectangle 1. You will check, let's say this is your rectangle 1, and then you will check the rectangle 2, and you will sum them up, right? You will sum them, sum both the moment of inertias, but about x-axis, right? Not about centroidal axis, about x-axis. And then you will check the moment of inertia about y-axis. You will do this and show me in your next class. I'll be asking any one of you to show me your copy. Show me your copy, and accordingly I will mark it. Takmil Shaukat. Who is Takmil Shaukat? Who is Takmil Shaukat? Fazan, who is Takmil Shaukat?
So one of the
Sorry.
students.
Huh?
So he's one of the students.
Okay. Please make sure and usually have a check on your this participants, because I have heard that many a times these passwords get leaked and some random people get joined in, which make chaos the class. Okay, this was your first problem. Then your one more problem is here. You have to find out the moment of inertia of this section about an axis which is passing through the center of gravity. You have this cutout circle which is 150 mm, and this is 100 total, and this is 300. You have to find out the moment of inertia of the hollow section. Which is hollow section? This is your circle, is your hollow section. Okay, this is hollow section. About an axis which is passing through its center of gravity. You have to find out moment of inertia of hollow section about an axis passing through its center of gravity or parallel to x axis, and its total width here is 200 mm. Now we have one more topic here. It's a subtopic of the same what we have been doing, which is a mass movement of inertia. Can anybody tell me what is mass moment of inertia? I had already described what does mass moment of inertia mean. Anybody? Sahil, what is mass moment of inertia? Zarka, you tell me what is mass moment of inertia? Zarka, are you able to hear me? Zarka, are you there?
Yes, sir.
Tell me what is mass moment of inertia?
So I don't know.
I had already talked about this in one of our previous classes. I had
So ability
already
of a
told you. Huh?
so as far as I remember, ability of a solid body to resist rotation about a particular axis.
Okay. Okay, fine, good. It is actually when we talk about when we are calculating the moment of inertia of any body which has a mass. Simple, in simpler words. This mass moment of inertia, it is actually the measure of the body's resistance to angular acceleration. It is actually of any mass moment of inertia is actually what it is a measure of the body resistance to angular acceleration. It is quite simple to area movement of inertia. What we used to do until now, we used to calculate area. We used to calculate the movement of inertia on the basis of its area, right? For any plane figure, we saw what will be the area, and that was simply called as area moment of inertia. Now, mass moment of inertia is quite similar to area moment of inertia. In area moment of inertia, we used to calculate the moment of inertia on the base of area. In mass moment of inertia, we will be able to calculate the moment of inertia on the basis of its mass. Okay, on the basis of its mass. Since this is basically used in dynamics actually to actually check the rotational motions. Right, we have rotational motions. We have to study rotational motions in dynamics, which will be of your in your later semesters, maybe in 6, 7 semester, wherein you will be studying dynamics and you will have to go through these rotational motions. And with the bodies in which we have masses, on the basis of which we have to calculate the moment of inertia. Let's say, for example, if we have a simple body and we have a mass, and the mass is categorized in that body. Let's say we have any axis. Let's say this is our z axis, and it's a wrist body, and we basically define the mass moment of inertia of any body in, let's say this is our z-axis. Let's say again same, we chose a small elemental or a small arbitrary element. What is this? Any arbitrary element. Arbitrary element, like the way we used to choose dA. Here we will be choosing dm. We will be choosing dm, any arbitrary element dm. Okay, here again in any body we have chosen an arbitrary element dm. So now within any axis, let's say this axis, let's say this will revolve, uh, this will revolve in this complete direction, and we say, let's say it has a distance or r, it has a radius of r within which this whole arbitrary element will is actually going to revolve, and we have to find out what moment of inertia. Then in that case again, your moment of inertia will be equal to integral of dm, right? dm is what? Elemental area times r square, as we used to do it in areas. In area, when we were calculating area, we used to say it is moment of inertia is simply equal to dA times the radius square. Similarly, here we have dm here, elemental mass, and r is the, what is r? R is basically the radius in which the whole of this arbitrary element will be revolving. It will depend upon the body now on which we are actually calculating the mass movement of inertia, and accordingly we will be having different r's for different bodies. Now the axis which has to be chosen here, that axis should actually pass through the body's center of body's mass center. Now here we have to calculate mass center, right? We are not calculating area, we have to calculate mass center, where will be the center of mass lie now. Okay, that needs to be chosen. And here what will be our common, we were actually talking about mass moment of inertias. So now that we came to know that here what we have to do, we have to replace the area with mass now, and we are actually checking it on any arbitrary element dm, right? And then we will integrate it for the complete circle for which the moment of inertia is to be calculated about any unique axis, right? If this is for z axis, we can check it for x axis, we can check it for y axis. It depends upon whether the object is a 2D object or it is a 3D object. And if it is 3D object, then we have to check it in all three of the axes, that is x, y, and z axes. And now, and about the center of the, about what? Mass center. We have to take into consideration that the axis which is chosen passes through the body's center, mass center, right? We are talking about mass center now. Now, let's say for this very body which we have already seen, this was our body, and we saw this is our elemental area, and this is our R, this is dm. And now we say if we are actually calculating the mass, then density has to be taken into consideration, right? When mass is there, density is associated with it. Rho, let's name that as rho. Then we can say the elemental area dm is actually equal to rho times dv. V is your volume and rho is your density. As you must be knowing that density is equal to what? Volume by change in volume by change in, sorry, change in mass by volume. This is density. Now, your elemental area dm will be calculated in terms of, dm will be calculated in terms of rho times dv. Now, why rho? Because if the body is having the, say, density throughout, then a rho does not have any role or does not have any significance. But if you have a composite section, right? Composite section will include a cylinder and a sphere, a cone and a sphere, and there you can have two different densities of the metal, right? Then in that case, you have to take into consideration the different densities. Now that here we are discussing for planar frames, wherein we have the same density of, say, same density. So we can simply write our moment of inertia, the body's moment of inertia in will be now calculated into volume elements. That will be equal to the moment of inertia will be now equal to integral of r square rho dm, rho dv, sorry, rho dv, and integral will be in terms of volume. Okay, and now if we have a rho as constant, if density is constant, we can write moment of inertia is equal to rho times integral r square dv. V is our integral. And now the mass has changed to what? Volume, right? Mass has changed to dm has changed now to dv. We can simply check the volume of any element and integrate it within the volume, and integrate it within the volume. So this will be our formula in order to calculate the moment of inertia, mass moment of inertia, which is what? I will be equal to rho integral of r square dv. Let's say we will do a simple example now. Let's say we have this cylinder, a simple cylinder is there. We have a cylinder, it has height h, and let's say this is our one axis, z axis, and let's say this will be h by 2, this will be h by 2, and this will be our capital R, okay, radius. Now here, let's say we have to find the mass moment of inertia about let's say this is z axis. Let's say this is z axis. We have to find out the moment of inertia about mass moment of inertia, mass moment of inertia about z axis. I have to find out mass moment of inertia about z axis, and rho density is constant. Density is constant. Now this problem, it is basically, it again will be solved in the form of shell elements, right? Because these cylinder, these cones, spheres, they are usually shell elements. Their mass moment of inertia is again calculated in the form of shell elements, and thus the single integration is to be used. Now here the volume, first of all, what we have to calculate, we have to calculate the volume, and we consider here, in order to calculate the mass moment of inertia, again we will be let's say take, we have considered one element. This is the element which we are actually considering. Let's say it is dr. Dr is the element, okay, and it is at a distance of small r. This distance is r, and we have chosen an elemental area dr, but it has a circle of complete circle of radius r, for which we are actually calculating the mass moment of inertia. We cannot calculate for a single point, right? We cannot calculate it for a single point. What we will do, a complete circle for this cylinder, this is a shell element, and then we will integrate it from 0 to complete r, right? We will integrate it from this axis. We are actually talking about z axis. So we will integrate it from point 0 to capital R. Capital R is the total. Capital R is what? Capital R is total radius, and small r is what? It is actually the radius of elemental mass, right? So how we can calculate the mass moment of inertia here? We need to consider dv of this elemental area. Fine. And now dv will be for this elemental area. Firstly, it will be circumference, that will be 2 pi r small r. I'm talking about small r. 2 pi r multiplied by height. How much is the total height? Total height is h, right? Multiplied by the thickness, 2 pi r into dr. Thickness is how much? Dr. That means your elemental volume of this elemental area dr is 2 pi r circumference into height into your thickness of that area. So this is so and so its mass is, so we can simply calculate its mass will be equal to rho times 2 pi r into height into dr, right? So when we have to integrate it for the entire element, right, that basically lies at a distance of r from which axis? Z axis. Then the moment of inertia will be, when we are for entire element, which lies at the distance of r, that will be d I r, sorry, z. D I z will be equal to r square dm, right? When we talk about for the entire element lies between r from z axis, then for that elemental area the mass moment of inertia will be equal to r square dm. Now we know how much is your r square is as it is, and dm is how much? 2 pi r h dr. That will be equal to 2 pi h r cube into rho also into dr. Fine. Now we have to integrate it over the entire cylinder. Integrating over whole cylinder. Therefore, you can say your Iz will become integration of mass r square dm. That will become a rho will come out constant, 2 will also come out constant, h is also constant, it will not change. That means integral of 0 to capital R r cube dr. So your Iz will become r cube will become r4, 0 to r. That will be a rho pi r raised to the power of 4 into h divided by 2. Okay, this is your mass movement of inertia. Now, actually, since the mass of the cylinder is what? Total mass of the cylinder will be what? That will be m. That will be integral of what? Dm of total mass, right? That will be dm. We can write that also in this way. That is rho 2 pi h integral 0 to r dr r and integrated, that will become r square to r integration of r will become r square by 2. That means it will be rho 2 will cancel out, pi h r square. This will be equal to m. So your mass will be equal to rho pi h r capital R square. Now putting the value of m also, iz will for this section, iz will become as iz will be half of m r square. This is your moment of inertia, mass moment of inertia. Is that clear? This was your mass moment of inertia. Now you can do one more problem here, which is homework for you. You have to find out the, let's say we have this plate, we have a plate, this is plate, and it has a density of, you have rho is equal to 8,000 kg per meter cube, density of this plate, and it has a thickness of 10 mm. Thickness how much? 10 mm. You have this plate, okay, having a thickness of 10 mm, and we have to determine its mass moment of inertia about an axis which is perpendicular to the page. Perpendicular to the page means in this particular axis. We have to find out I moment of mass moment of inertia, IM mass moment of inertia about an axis which is perpendicular to the page. We have to find out that. Okay, and it is passing through the point at O. Now, where is that O? That point is here, O. This is your point, O. And your small radius R is 0.125 m, 0.125 meter, and capital R is 0.25 m. Okay, now here you have to find out mass moment of inertia. I'll give you a hint what you will do. Firstly, you will see what will be the what will be the mass moment of inertia of the outer circle, and then you will deduct the mass moment of inertia of the inner circle. Simple, nothing to do. Outer circle mass moment of inertia, and then deduct or subtract the internal mass moment of inertia of the internal circle. It is at this point. Sorry, you have to keep calculate at point O. Here is your O. It is at the bottom of the, where is it? It is actually at the bottom of your any reference line, bottom of the circle, wherein from where you have to calculate the moment, mass moment of inertia. And this is again homework for you. You will have to do it yourself. Okay, this is all about today's lecture. We have completed this chapter. I'll be giving you a tutorial sheet which you will be